Some of you might have noticed that Franco just told me a little secret that he has added a new device that after the second bit, still the speaker doesn't come out. A little trap door he has added. So, I would like to remind speakers, and we have already had a very effective chairman here yesterday, Mike Cooper, and I spent 6 months with Mike in SRI and I learned all the tricks of the trade. So please be cognizant. These I would like to call the first speaker this afternoon, Professor Arata. And Dr. Arata, please. Same time, I'm not going to announce the title of the paper, we'll leave it to the speaker. He will be held by Chairman Uzam.
Co-worker, co-researcher, Professor Tan, this is the principle of our sono implantation system. We apply ultrasonic wave to enclose vessel and working liquid of litho or HO were placed together with the metal coils. The working gas was carbon and nitrogen. The vessel was buttered to gasoline, the working liquid. The right shows snow powder. A is one example of original skewer scale. When sono energy is given with 300 watts using generator of 600 watts and 19 kilohertz. Silver scale was broken into fine powder, about 10 to 120 hours. The first, we used mini metal. You can see the strong sono implantation effect of hydrogen or deuterium given to all of the metals. As a second, one typical very important example is shown as follows. Namely, sono implanted effect of litho working liquid for a gold coin was stronger than over 10 times of HO working liquid. In other words, deuterium can be intensely injected into solid than hydrogen. It was a surprise event for us. This is a bar graph of mass number 1 to 50 emitted gamma sheeted samples of sono implanted metal. When we see blue and open bars, we can understand intuitively that intensity of the implantation is intensely stronger H implantation. Working gas effect was also tested. We have used argon, nitrogen, helium, and neon. The results show that the working glass also was implanted strongly to metal coil or powder. The first, this shows some implantation of pure helium into paradigm foil within its working liquid. We can see these are almost zero. The Lerici is very low, but the helium-4 is very high level. This means that the strong injected helium is much stronger than deuterium. And the second, this working gas is
Over.
3 minutes over.
Where's the poster? We got the
So I
poster.
think,
I see.
Okay.
next speaker, Dr. Chernow. Dr. Chernow, please.
Title my poster is what to look here. Aim of research. It is study to role of the diffusion processes in the isotope composition, change of metals during hydrogen charge. For this purpose, we measured isotope composition in titanium, lithium in titanium, palladium, and thermodiffusion, copper, and in nickel. And also some metals. We observed as a result enough strong change, isotope change, for example, lithium in titanium. It's about 30% for lithium, 6 and 7. And we observed during isotope effects in thermodiffusion copper and nickel when we create in attention stress in lattice of nickel. In this case, we observe strong change isotope. But if no loading, no attention, we did not see some isotope effects. Our opinion that in process of the charge, hydrogen charge metals, isotope change composition takes place, but mechanism, it is more than, it is diffusion process. Hydrogen plays a dual role in this diffusion process. Firstly, it stimulates atom diffusion. Secondly, while enriched specimen, it causes stress and crystal lattice. We have a lot of information about it. For you, it's possible to look. These experiment results, I invite you for my poster, and it's possible to discuss with which. Thank you very much.
The next speaker, Dr. Chikia.
How many people in this room have ever detected neutrons in a cold fusion experiment? When this happened, were you excited? Didn't you want to tell your friends and colleagues about it? First of all, I developed a simple surface activation procedure that enables the achievement of very high deuterium loading ratios in titanium. Then, I tested both the surface activation and the gas loading procedure, and they provided a reproducible way of achieving high loading ratios. I performed experiments of loading titanium slab samples from the gas phase. I monitored neutron emission from the samples during and after the loading. After loading the samples, during cycling the temperature of the loaded samples up to 800 degrees Celsius and down to liquid nitrogen temperature. During the experiments, I detected neutron emissions in bursts significantly above the background, randomly distributed over the time span of the experiment. This proves that neutrons highly loaded in titanium samples under non-equilibrium conditions undergo nuclear reactions revealed through their signature, that is neutron emission. I am confident that in the near future, somebody in our field will lay all doubts to rest, proving that we have all been on the right track. Thank you.
Oh, good.
Thank you very much, Didier. Dr. J.J. Dufour.
So I first define what Hydrex is not. Hydrex is not an hydrino, Hydrex is not a virtual neutron, Hydrex is not a result of proton-electron fusion. Hydrex might be a metastable chemical resonance between a proton and an electron of nuclear dimension, few femtoid, very long lifetime, second compared to nuclear time, which absorbs a few eV when formed. What are its possible properties? It's a small electrical dipole, a small permanent magnet, and it's easier to obtain than its deuterium counterpart because of the value of the magnetic moment. What we suppose is it could form a cluster with a big nucleus surrounding these nuclears and give a kind of compound nucleus that like you consider in normal nuclear reaction. And in this cluster, in which the equilibrium between the proton repulsion and the nuclear force will be modified, you could have a rearrangement yielding a smaller nucleus and a number of helium-4 particles. You can make some calculation, some mass, some balance for the proton and electron, which we have done, and then you arrive at a certain energy release, which ranges from 200 MeV when you start from uranium to 30 MeV when you arrive to palladium. And from time to time, you have some smaller channels exit, which are, for instance, lithium-6, helium-3, etc., which depends on the parity of the A' and ZZ'. I don't enter into detail. I just want to finish with a small graph of what might be this thing. So, in fact, we consider a number of hydrex surrounding a nucleus, in which you can have, of course, enhanced alpha emission, but the excess of neutron could react with the proton present at nuclear distance, giving also alpha particles, and you are left, finally, you are left with a stable nucleus, because you have taken away the excess neutron. You are left with a stable nucleus and a number of byproducts, which are alpha particles, and in smaller amounts, helium-3 or tritium or small things like that. And when you make the balance, my conclusion that from uranium you would get 200 MeV, and from palladium some 35 MeV. Thank you.
Virtual trapdoor has had an effect. Mr. Goriacha.
Up and down.
Dear colleagues, the work under presentation refers back to 1979. The experimental layout is shown on the screen. The condenser was assembled of polyethylene sheets of special chemical composition and 21 thin electrodes. The N-tube generated pulses of 14 MeV neutrons. The results of the experiment are shown in the picture. It was determined that more than 50% of gammas registered at the moments of the gamma neutron splashes appeared in the vicinity of 25 to 30 megaelectron volts that could only evidence their origination from nuclear reactions of fusion. In order to get convinced in the reality of this assumption, an additional experiment was carried out. The schematic layout and the results obtained are shown in this picture. Following the results of these experiments, we elaborated a theoretical explanation of the phenomenon observed. In our opinion, it opened wide possibilities for obtaining brand new practically useful technologies. Based upon those phenomena discovered, we have been carrying on experiments in various directions. During last 20 years, excluding 5 years of my staying in Salt Lake City, where I used to work for Honorable Hale Fox and unforgettable Fred Jagger. All those discoveries now have resulted in creation the basis for developing a number of extremely promisable projects. Among them are the following: strong decreasing gamma transition through matter and increasing gamma reflection from it. Enforced deactivation of radioactive materials. Controlled decreasing interaction of gravity field with matter and screening the field of gravity. A radical increase of resistibility of sensitive electronic elements and optics against radiation. Gamma propagation along band ducts. Initiating low-energy nuclear reactions. Multiplying neutrons and gamma quanta. Direct converting solar energy into electricity with previously unachievable effectiveness. Generating nuclear energy using deeply subcritical assemblies, and many more. And the last, but not the least, in all those projects, we are ready to cooperate with anybody, and we are looking forward to meeting any of you at our Kurchatov Research Center in Moscow. Thank you.
Now on to the next speaker, Dr. Ota.
Thank you to be here. My name is Masayuki Ota. I'm a member of Takashira Osaka University, Japan. The title is Possible Mechanism of Coherent Multi-Body Fusion. Multi-body fusion model has proposed to explain cold fusion phenomena. This model assumes that the multi-body fusion reaction rate is enhanced in the transient process by the continued motion of 3 or 4 hydrogen isotopes in palladium lattice. It can be considered that the symmetry of hydrogen isotopes in palladium lattice realizes the situation inducing these reactions. This time, we propose a possible mechanism of multi-body fusion from 3 points of view that I'd like to talk about. first one is a coherent motion of hydrogen isotopes in palladium lattice. This figure shows two-dimensional schematic view converted from tetrahedral structure of hydrogen isotopes in the previous figure. In each figure, arrow shows the direction of oscillation of hydrogen isotopes at any time. These modes may realize strong electron-phonon interactions to induce 3 or 4D reactions. The second is electron-phonon interactions. It is known that for high loading ratio of palladium H or DX, electron-phonon interactions become strong and optical mode contributes to electron-phonon interactions. Because of electron-phonon interactions, electrons at film surface become heavy in metal. Then the density of state near film surface is enhanced by the factor 1 plus lambda. Third thing, electron-electron interactions. Electron correlation is remarked especially in palladium. Effective mass near film level become also heavy, so the density of state near film surface is enhanced. Therefore, the effective region of growing potential becomes to be reduced. For the transient condition in palladium DX, if more large effective mass is realized, it can be more approached. Also, low-energy fission model was proposed by Professor Takashi to explain nuclear transmutation. The origin of coherent match-body fusion and low-energy fission may be the same low-energy photon. Thank you.
Thank you very much, Dr. Next speaker will be Dr. Karaput. Dr. Karaput.
Analysis of experimental results on excess heat power production in nucleus yield in the cathode material and penetrating radiation in experiment with high current body charge. Excess heat power production achieved amounted up to several 10 watts with efficiency up to 150% and even higher. Yield of diffusion nucleus with change by several tens of times natural ratio of element isotopes was updated. The main impurity nucleus are gamma emission demonstration was carried out. Gamma emission ranging 0.1 up to 3 MeV were observed. When the glow discharge was in the course of up to 8 days after the discharge, current switched off. The main contribution to gamma emission radioactive nucleus impurity yield up to 10 to 5 of atoms by beta radioactive change with mass. The X-ray emission radiation was carried out. The overall X-ray irradiation dose for 6 hours of the experiment amounted to 5,000 Röntgen. Registration result allow to single out spectrum area with energy of 1.5 up to 2 kiloelectron volt. The obtained experimental result allowed to consider the possible mechanism for processes in the cathode material solid. They are as following. Deuterium-ion acceleration in glow discharge near cathode area to energy of several hundred electron volt. Non-receiving processes of deuterium-ion collision with the crystal lattice ions. The polyoptic polyphenol is formed. Non-linear processes per or for order in beginning. This condition at the density corresponding to solid energy several times intensity of nuclear reaction high energy. This possible type of nuclear reaction is following.
Thank you, Dr. Scaramuzzi. The next speaker, in place of Dr. Arai, who is listed, Dr. Kojima will speak.
My presentation today is nuclear transmutations in solids, explained by ICCF model by many members of
What is TNCF?
my former laboratory. TNCF model is proposed at ICCF-8, 1993 October. And in this almost 7 years, the model evolved and enriched its content. Recently, the first original assumption of the trapped neutron was used to predict existence of neutron drops. It means neutrons and protons condensated at boundary regions. I have to apologize about the misprint in the abstract of my paper. Mismatching of my brain and Microsoft Word program. The 6-time sodium 10^11 became like this in the manuscript. The result we obtained was listed here. And in 1992, Bush perhaps the first measurement of the nuclear transmutation by decay, we call it, because the production of the new element is consistently explained by the decay of a new element formed in the material absorbing one neutron. And after this time, many data was appeared, and not only by the decay, but also fission results were observed, and we can discuss this problem in my booth. Please come and discuss with me. Thank you.
Thank you. The next speaker, Dr. Lipson.
I'd like to present full data on the study of latest induced nuclear processes, in particular nuclear emissions in palladium oxide, coal infrastructure that were obtained for last 8 years. This work has been carried out with participation of Russian institutes of physical chemistry and Lerici Physics Institute Russian Academy of Sciences and Japanese research groups from NHE laboratory, Osaka and Tohoku University. We investigated the process of exothermic deuterium desorption in this heterostructure. That was loaded with deuterium by electrolysis. As a control one, we used the same heterostructures that were loaded with hydrogen. The neutron measurements were performed in low background laboratory using ME213, two independent detectors. The spectra after background subtracting of background from hydrogen loaded samples, you can see here, and you can see a clear peak near 2.45 MeV for both detector used. The level of neutron emission is not so high and is close to Jones level. So about 2 multiplied 10 to minus 23 per second per PD pair. Near the same the level of proton emission of 3 MeV proton that we observed using surface silicon barrier detectors and CR39 trace detectors. Also, we saw the long-range alpha particles with energies till 12 mega electron volts. Anyway, we can conclude that lattice induced nuclear reaction processes in non-equilibrium deuterated solids are really observed in our heterostructure as a result of exothermic deuterium desorption. Thanks for your attention.
Next speaker, Dr. Nassisi.
In this work, we have studied the transmutation of the palladium when this is loaded with deuterium. And in particular, in order to understand when we have transmutation or more transmutation, loss transmutation, we have used palladium film of variety richness. The experimental paradigm we have used in order to perform this experiment is an ISCMNS laser and small stainless steel chamber. The film is in the chamber, and the total pressure, the maximum pressure of the deuterium was 2.4 bar and 5 bar. Not all sample, but just a small sample we processed by a single laser with 400 shots for a week for 5 weeks. After 5 weeks, we have analyzed the sample. The films were modified with many cracks. I'm sorry because we have the slot, with many cracks and with the central part and a large bubble of about 2 micron. In the center we have found many elements. These elements are dependent of the pressure and of the
thickness of the film. In this row we have put the element. The number of elements are this one, where we can see that increasing the thickness of the film, the number of elements in the bubble is increasing. And the percentage of elements as a function of atomic number for the A case, where the A case is the film processed with 2.5 bar, where this one, where the maximum of atomic number is near 14, 15, or another peak near 28. The large one is this concentration.
Dr. Natoya, is she here? Okay, yes, Dr. Natoya, Dr. Scaramuzzi.
Well, this is a new experiment we have started in Frascati, and you see that by the title, it's an experiment in which we want to study the gas loading of palladium in deuterium while changing temperature, and hopefully also see something more like heat effects. This is just to give you an idea of why one wants to study this changing temperature. You can see from this graph that the charging ratio is a function of temperature, in the sense that when you go down in temperature, you charge more deuterium. Also is a function of pressure, so you charge more deuterium at the high pressure. So the idea is to try to obtain high charging by decreasing the temperature. Of course, when you decrease the temperature, you have also an effect in decreasing the coefficient of diffusion. And so in order to compensate this fact, we are using very thin film of deuterium, of palladium. But you will see the geometry when you come to stand. This gives you an idea of the solution that we choose in order to obtain temperature decreasing by steps. We start with a closed cycle refrigerator, which can give temperature from room temperature down to 20 or even 10 Kelvin. And we have constructed a system with shields in such a way that in the shield, what is called the copper shield, can assume any temperature from the minimum to 300 Kelvin. And the cell, the experimental cell, which is within, is kept at about 10 Kelvin above the temperature of the copper shield, so that you have to heat it up in order to keep it constant temperature. And but it sees only something at constant temperature. It's very easy to thermoregulate at that point. Just to give you an idea of the first attempt that we made is the stay. This is just the first step that we made. It's okay. The upper graph, the scale of temperature is the same. The upper graph tells you how the temperature is constant. The temperature is constant, and down you can see here the heat you need to keep the cell at the same temperature of the sheet is 343 milliwatts. But as soon as we apply heat with another heater, you see the temperature is very little change, and then it comes back to the usual temperature state. And well, the rest when you can. Make an announcement, nothing to do with this. during the coffee break, morning coffee break, of course, there will be the possibility to take a picture of all the people participating in the conference. And the picture will be inserted in the proceedings of the conference. Who is interested in getting a copy of the format 20 by 30 centimeters can ask for it in the desk downstairs. It will cost 10,000. Excuse me for the interruption.
All right, next we'll hear from Dr. Arata. We have a substitution here, Arata.
Doctor, Muhammad.
The research of tritium generation for long interaction of hydrogen isotopes with a solid in condition of thermal activation, both in stationary conditions and in dynamic mode, for transfusion of hydrogen isotopes through heated up membranes. The long endurance of hydrogen, about 3 years, is established that in heated up to 820 Kelvin in metal does not result in tritium generation. The accumulation tritium in passive hydrogen and deuterium through the heated up metal membranes is fixed. The specific rate of tritium accumulation in deuterium exceeds a rate of its accumulation in hydrogen almost 3 times. That testifies to a possibility of tritium generation in deuterium not only at the expense before accumulated, but also at reason of the nuclear reaction. Thank you very much.
Next speaker is Dr. Volante.
This takes some time. They have lost time in this.
This work is a finite element modeling for the matrix experiment and has been done in framework of cooperating work with SRI and INFM. I am Violante and I am from NEM. As you have seen this morning in the the presentation, matrix experiment has been designed to reveal the correlation between excess of it and helium production. In order to have better accuracy in this evaluation, we have done this model in order to estimate the increasing of the temperature of the active bed when we have excess of heat production correlated with helium core production. As you have seen, we have this cell that is the domain over which we have to integrate the heat transfer equation with proper boundary conditions that are covering the convective heat transfer with the radiative heat transfer at top due to the high temperature of the system. And this introduces a non-linearity in the description of the system. But before doing that, we have to find an evolution law for the environmental temperature that is oscillating in about 1 degree along the experiments. So by developing in Fourier series these experimental points, we have these red cubes passing through the experimental point, that is the law that we are looking for. You see that the excess of heat production is very clear, because we have this separation between the dark cube and the red cube here, that is about 0.7 centigrades for 0.1 watt of excess of heat produced. But we have to filter the effect of the oscillation of the room temperature that can be done on the basis of calculation, because this effect is in the order of 0.2 centigrades. So we have 0.7 centigrades plus or minus 0.2 centigrades. So the effect is very clear, and we can conclude that this simulation confirm the experimental value and say us that the system is sensitive enough to reveal an excess of heat of 0.1 watt. And we can state that the excess of heat of 0.1 watt with palladium staying inside the system is in the order of 27 watt per cubic centimeter of palladium as density of vapor. Thanks.
The next speaker is Dr. Wang.
Yesterday, I have introduced something about the beam-solid interaction, the low-energy nuclear reactions. But today, I will talk about the analysis of the sample. And we have used the nuclear reaction analysis and also SEM to observe the surface effect. Now, I show you the picture. This is 10,000 times SEM pictures. This is just before the titanium plate, before charged with deuterium. And this is after charge. You can see the size, a lot of the small size grains of the titanium. The size is about 100 to 200 nanometers. And we have used the implantation methods to charge the deuterium into the titanium. You can see the curve is not continuously increased. Yeah, step by step, then sometimes decreased. The density of the deuterium inside of titanium decreased, then increased. All the tendencies increased, but sometimes decreased. And we have used the target and bombarded with the deuteron beam. This is before the bombardment, this is after the bombardment. You can see there are serious segregations of the sample surface. Then you can find a lot of the small size of bars. The size is about 200 to 500 nanometers. We have also analyzed the containment of nitrogen-15 inside of different samples. We found in the titanium deuterates, the containment of the nitrogen-15 is very high. And also, we use this is old target. We use a fresh target. There are also a lot of nitrogen-15, but the contents is lower, a little lower. Titanium and other samples is two odds lower. We can give such conclusion. Titanium deuterates can trap nitrogen-15, and after the loading of the deuterium inside titanium, the titanium metal change our finish. Thank you.
The next speaker is Dr. Zhang. Dr. Zhang here?
No.
No? Okay. All right, next speaker is Dr. Huh? Oh, there. Are you?
No.
No. All right, well, then Dr. Spallone.
Spallone.
Well, in this poster, we present an experimental protocol to achieve a very high overloading. This is the continuum of Celani's talk. I mean, Mr. Spallone. And we have this question. What's the main problem of electrolysis cold fusion to reach electrolysis cold fusion? The answer is, of course, to overload the deuterium over palladium, and how to do. And we, in a couple of years, we found this procedure. We refer to the Baranowski-Lewis curve with respect to the resistance. This curve is common most of you. And this is the procedure we are using, the detail of the procedure working, before and after the beginning of this procedure. And at the end of this procedure, some days later, this is the final goal. It means we are here, literally is at this point, okay? Finally, we try with deuterium to use the same procedure, but as Celani said in his poster, we have problem with the purity of heavy water. But in conclusion, hydrogen over palladium, according to us, is a goal achieved. The problem is deuterium. We are right at this point now with the deuterium. And let me show this table. These are last data, preliminary data of the last weeks, and results are encouraging right now. Thank you.
Next is Dr. Afanishchev, if I'm pronouncing that right. Is anybody here anywhere close to that pronunciation? All right, next is McCarty. Dr. McCarty is here.
Our poster presents some effect which refer to nickel-hydrogen system. In particular, we have an example of hydrogen loading in nickel from gas at this value typical, about 700 Kelvin for the temperature and 200 millibar for the pressure. The dependence of the loading rate from the temperature. The method we use to measure power production. One cell produced 900 megajoule in about 300 days. An example of neutron emission from a cell, the amount of neutron was about 6,000 neutron per second, measured by gold activation, detecting the gamma ray from the excitation. The emission of gamma rays at this energy 660 keV from cell. The spectra ADAX showing elements. This is there are some elements, but many other are existing in other spectra on the nickel surface after experiments, and the tracks of charged particles ionizing more than electrons observed in a diffusion chamber. Thank you.
Next is Dr. Sinha.
In this paper, we consider screening by electrons, and we will finally facilitate the two neutrons coming close together in the metal neutrides. In addition to the bound states of electrons, electron pairs on the neutrides and on molecules, we consider a polarization response arising from monopole-dipole interaction. And we will see that the second order gives a fairly appreciable contribution. The Hamiltonian, the kinetic energy of two neutrons, potential energy, and the energy to solve the electron problem. Then we have the higher order terms involving the charge of the electron at a palladium metal and the charge of the neutron 1, and then higher order the charge of the palladium and the neutron 2. And so this is another reverse process, so we have two terms, and this affects the consider. The calculation is complicated, but I'm quoting the final result. The second order correction consists of a constant term EC and the metric element, the polarization operator, into 1 upon Rm's dimension form. Rm means the distance from the center of mass of neutron pair to any one of the metal atoms. And this comes as the first one, then the distance between the two neutrons by half, and the center of mass distance to the metal layer squared and to the fourth power. And we find that for this constant EC is about 32.2 electron volt. We are writing the AB is the Bohr radius, I is the Rydberg energy, and A is the Armstrong unit. Then we find that this PM squared can be of the order of 1.5, 1.7 or this kind of so. So we estimate the numerical values of this is about 12 electrons for palladium and minus 10 for this. This besides the screening due to the bound states. For palladium, our conclusion is that we must have higher effective mass of the electron coming for a software interaction or the exchange, correlation exchange effects. And all these subtle points I will explain on the poster, whoever wants to know.
Thank you very much. Moving on, the next speaker is Dr. Urkov. Here.
I'd like to present the potential fresh integration. The patent I received this year. The title of patent is Method of Nuclear Fusion and Device for its Realization. The method is based on titanium leading with deuterium air mixture and the temperature about 550 degrees centigrade. The air contained in the mixture is less than 4%. The main idea of the method presented is concerned to suggest that nuclear reaction occurs between not only DP pairs but also between deuterium and oxygen. In this case, the neutron gamma emission and excess heat are observed. The sample used is a titanium hydrate pressed from the powder with a particle size on 100 micron. The hydrogen has to be removed from sample before put in setup by the thermal desorption technique. The device consists of reaction chamber, operating sample, block of sample degassation, heater and cooler, pressure gauge, and thermocouple. The invention could be also used as a source of neutrons and gamma radiation, as well as for radioactive waste neutralization and excess heat production. Thank you.
The next speaker is Dr. Nasikas.
The title of the poster is The Cold Fusion as a Space-Time Energy Pumping Process. The purpose of this work is to explain the cold fusion phenomena on the basis of the hypothesis of the quantum space-time, QST. This hypothesis is based on the unification of the physical meaning of the notions which derive either from the general relativity theory or the quantum mechanics. An experiment is proposed to verify this cold fusion explanation. According to this hypothesis, we have that during the approach between electron and proton, a gravitational space energy absorption takes place. According to Mills, there exists a stable state named hydrino under the first fundamental electron energy state in the hydrogen atom. Mills' experiments can be explained on the basis of the quantum space-time ether absorption during the electron-proton approach through unstable states. This is an alternative explanation since hydrinos have not been detected. All these concern excess heat without any reaction. The reactions in cold fusion phenomena, according to an explanation mentioned by Mizuno, can be done on the basis of the reaction between electron and proton or deuterium with products neutron and neutrino. These reactions are endothermic, and the energy of 0.783 mega electron volt is difficult to be handled
by means of low voltages. Thus, it is expected that these reactions are facilitated by a gravitational space energy absorption during the approach between electron and proton. Concerning the proposed experiment, according to the QST hypothesis, the attraction of an object is attributed to the fact that the quantum space-time ether under the object attracts the object more than the upper one. If we reduce the quantum space-time ether density under the body, then a weight loss will take place. This can be done by means of an arrangement which consists of a nickel plate with a hydrogenated area at its lower point. Negative voltage electric pulses are exercised on this plate, having as a result quantum space-time ether absorption at its lower part and weight loss which can be measured. Thank
you. That was the last speaker. I want to thank the speakers for staying within the allotted time, even though it's practically impossible to explain anything in such a short interval. Now you have a chance to go downstairs and find out what they actually said. We'll see you again tomorrow.
You can invite yourself.
Oh yeah. Oh, that one.
Passing messages. Can you give me the address? No. But if you send me an email, I can send it. The problem is my email is always disconnected. No. I sent you email, never answered. No, never sent it to me. I sent him one 3 times. Give me your email address. Let me give you
It's unfair for the chairman of the session, because of their inability to make machinery work, to take it out of the height of the presenters. You wouldn't do that, would you? No.
Good morning, ladies and gentlemen. We will start the morning session. I am Joe Kasagi from Tohoku University.
I'm Scott Chubb from the Naval Research Laboratory.
We will chair this session. And first speaker of the session is Professor Arata from Osaka University. He will talk about his brain cell. And this talk, it will be 30 minutes. So I will tell you just before 5 minutes before the end.
I have to keep my head over here. So. That's not a good idea to put your hands up too often. After you get whacked on the back of the head by.
This is our big presented subject here. In VS means the double structure cathode. What means the bulk cathode? Litho and exo means use liquid. The first shows necessary function for a solid reactor. Now, experimental condition of solid-state nuclear fusion consists of 2 parts. That is fuel and the solid reactor are shown in the diagram. As far as fuel is concerned, pH and mixing D plus H have been used. In these fuels, effectively causes reaction, but H does not at all. In the case of mixing of D and H, D clusters are surrounded with H groups, like an alcohol cluster in the water, which is our expectation, as indicated in footnote in this diagram. So far, as a solid reactor, bulk solid paradigm has been used in most current experiments. But nuclear fusion scarcely occurs because of low content of the atoms in bulk radium, because of restriction by working only the diffusion effect. So, in our case, radium powders have been used. In these powders, there are 3 types. That is, large size one, whose diameter is longer than 1,000 nanometer. Middle size one, about 20 nanometer to 1,000 nanometer. And atom clusters, whose size is smaller than 20 nanometer in diameter, as shown in this figure. Here, it is emphasized that in these powders, only atom clusters effectively cause fusion, because the atoms absorb into atom clusters more than 150% atomic percent against palladium atoms. This is condition shown by large SHC in this figure. Namely, it is concluded that combination of the atoms and palladium atoms clusters is the best choice for solid-state nuclear fusion, as indicated with this flow chart indicated by the arrow. This is an example showing anomalous behavior of atom cluster. That is spontaneous mixing for polymer atoms instantly occurs when the size of particle is smaller than a critical one. Here, both microglass and corresponding to different diffraction rings at left and right band, right hand sides in upper and lower figure were taken before and after in sheets vapor deposition of copper atoms on atom cluster, gold atom cluster in high vacuum. Initial and final average size of atom clusters in these figures are 5 and 12 nanometer in diameter in this upper, and 20 and 21 millimeter in diameter in the lower, respectively. You see, copper atoms are instantly dissolved into gold atom cluster in the upper, in which all diffraction rings are expanded, but only cover gold particles in the lower, in which diffraction rings of copper only superimpose on those of gold particles. Namely, in the case of FCC metals such as gold and palladium, the critical size is about 20 nanometer in diameter. In short, gold clusters instantly absorb 150 atomic percent, even copper atoms as solute atoms, much more easy in deuterium atoms. We presentation as follows. Like this. The following shows the important function of double structure cathode called as this function. Item A. Item A. The extremely high pressure different H with higher than several thousand hours takes place easily inside this cathode by Siebert's law. Item B. Deuterium purity is extremely high inside this cathode because palladium less works as a filter. item C, deuterium distributes on the surface over powders instantly and uniformly by spillover effect. Item D, palladium black on the nanometer scale, that is atom cluster, absorbs an extremely high content of the deuterium already mentioned. This shows characteristics of palladium vessel. Right side figure shows relationships between inner pressure of deuterium produced in bars and incubation time, tau c, in hours, until when deuterium atoms are coming into inner space by electrolysis. Their relations are illustrated in lower right side. Left side diagrams is relation between increasing ratio of inner pressure and electric current density. In usual case, inner pressure increase about 30 to 50 bars a day. This is a closed cell system we use. Left side shows both open type and closed type VHS cathode. The right side shows our use. These diagrams are typical results obtained by using the closed cell system. The results have been obtained with 100% reproduced without exception. Upper data was obtained by closed system, middle day by open system, middle data by open system, and lower data with D2O and H2O using electrolyte, in which D2O is 2 times larger than H2O in weight. The latest data shows that the deuterium cluster surrounding with hydrogen group take place the reaction within palladium atom cluster. In order to know the difference between deuteron and proton as a fluid inside VHS cathode, 2 identical cells were constructed and connected in series electrically. And so only electrolyte is different. This shows definitive difference between D2O electrolyte and H2O electrolyte. Upper side diagram show that D2O generates much excess energy, but nothing in H2O. And lower side show that extracted sample in H2O cell released much helium, but nothing in H2O cell. In other words, because highly concentrated deuterium exists within VHS cell and highly concentrated proton exists within VHS cell, it is concluded that crowded neutrons within solid cause nuclear reaction, but the crowded protons within a solid never produce nuclear reaction. It is well known that the bulk solid was generally used as a cathode. We performed the experiment to compare the bulk cathode and VHS cathode, as shown in right side. Both cells, every conditions, it's same except the cathode. This is the experimental results of the excess energy. Right side is bulk V2O and left side is VS V2O. Anybody can easily understand that the distinct difference between both cathode in subordinate parameters, such as the excess energy, its ratio, cell voltage, cell input energy, and cell temperature. under the same current as the main parameter, which is the most important parameter because of carrier of the plus ion. This diagram was made in order to help easy to understand these experimental results. These parameters are shown chronologically by putting on top of each other. We report to proceeding more in detail. In order to investigate further the difference between the bulk cathode and DS cathode, we measure the deuterium concentration of both cathodes by using quadruple mass spectrometer. The first to make the sample powder of bulk D2O are shown in here. We drilled 3 zones of the cathode, such as the A zone is center, B is middle, and C is the edge. As shown in this diagram, 3 kinds of powder sample of bulk D2O and palladium black sample of the DS-D2O were heated under the same condition. As you can see, the spectrum shows these 3 zones in bulk cathode is no essential difference, and there is only a little D2 with no helium-4. On the contrary, in the DS-D2O, not only extremely large amount of D2, such as the continuous releasing time is over 10 times longer than bulk sample, but also emits helium clearly. This diagram shows one example of VI effect we developed. Indicates helium-4 existed in palladium black only, extracted from the DS-D2O cell. These diagrams show time evolution chart of QMS for the most important mass analysis, such as the D2 plus helium-4, Me22 argon 40. Upper left side, A shows background of the QM system, and argon gas only appears. B shows calculation by air. Here it is very important to know the ratio helium and neon to avoid the air contamination. C shows intensity of the same gases released from highly hydrogenated palladium black extracted from the H2O cell. D shows also the same gases intensity released from highly deuterated palladium black in the DS-D2O cell. Here, comparing C and D, it is concluded that highly hydrogenated palladium black released extremely low level of D2 and no helium-4. On the contrary, highly deuterated palladium black clearly released much component of D2 and helium-4, but there is no detectable neon-22. In these all experiments, we have measured helium released from only palladium black after long time evacuation to be 10 to minus 9 tall and heating, but do not measure for the inner gases inside the cathode. We developed, therefore, new detection system as shown in this diagram, and last year finally succeeded in capturing inner gases inside this cathode, included palladium black. Amount of all detected helium was much larger than over 100 times of released one of palladium black. These results were published to Japan Academy in last year, proceeding Japan Academy. Growth type DS cathode is measured by A-type system, and all type cathode is by the type system. In former method, DS cathode set up inside flexible FT tank, in which is evacuated to high vacuum 10 to minus 9 to 12, and then DS cathode is pierced to make small hole about 20 micron in diameter from outside. In that method, of course, of type B, in the gases of this cathode is measured directly during electrolysis. In this case, in the gases present pressure was almost monitored by a pressure gauge. Left side diagram shows a couple of spectra of mass 4 with B2 and M4 obtained by our developed closed QMS with A-type piercing system. When DS cathode was set up inside the tank with very high vacuum in the gases inside DS cathode, ought to lead into the tank throughout the cathode wall. This situation is the first stage before piercing and play a great important role in this experiment. When the gas pressure of this leakage gas accumulated in FT tank, because 3 told the leakage gas within 1.1 cc was introduced to QMS through the standard vessel. And after a rapid time, tau 1, tau 2, and tau 3, left top side, A shows M4, coupled spectral QMS analysis after different elapsed time, tau 1, tau 2, and tau 3. But we can see only this component and never fusion component. This means that leakage gas was only pure deuterium. This result is very important. And this determined quickly decreases because of beta action. After piercing, lower side B, C, and D were obtained at a different elapsed time, tau 1, tau 2, and tau 3 respectively. Namely, B is 1.1 cc, 34 immediately taken in a gas released from inside this cathode after piercing action. C 1.1 cc at 1.1 bar, taken at 5 hours after piercing. And B is 1.1 cc at 1.1 bar, taken at 134 hours after piercing. The right side diagram shows relation to voltage and current, namely real effect, for mass number 2, 3, and 4. Groups of released in the gases taken at 5 minutes after tau 3. This data corresponds to left lower side D. Here, elapsed time tau 1 to tau 1 200, tau 2 400, and tau 3 800 seconds are given. Top right side figure, A is for absolute current, and namely intensity and VAR 1, B is normalized. These results demonstrate that the group M2 contains D and H2 times M3 is found to be mostly HD, while the group M4 is named helium 4. This is clear. This is bar graph and demonstrates the basic characteristic of our developed closed QMS system, where mass spectrometer range 1 to 50. Red bar shows intensity distribution at the mass number using open QMS system under condition of 10 to minus 9 torr during pumping action. Blue bar shows characteristic of the closed QMS system, and open bar shows the inner atmosphere generating inside this cathode within closed QMS system. This demonstrates existence of enormous deuterium and much helium inside this cathode. And furthermore, it was confirmed that function of our QMS is essentially fixed. inner gas was analyzed continually through over 1 month, and exactly evidence the much helium hole. In order to make the promotion of practical use of excess energy, the first we developed controlling method to generate the constant output for the excess energy. At present, we are still parallel operation of 4 cells during several thousand hours. We show some examples in the first half of this experiment. We study characteristics of excess energy under the many kinds of conditions, and then after that we apply controlling method for the 4 DSB cells. They are now working under the controlling about 1 or 2 man. Lastly, we hope that this experimental data contribution to make the first step to be given promotion of practical use of the excess energy. Thank you.
Thank you very much, Professor Arata, and very nice data for the long time measurement, and nice improvement yourself, and nice result. And now this paper is open to discussion. Any questions? Yeah?
The power cell.
Okay, you got to conclude. Which one is the energy gain of the system? How much power you put in and how much out?
Energy gain.
Now about power.
How much?
At present, now about 10%.
10%.
Okay. I think Dr. Makure also agree.
And may I do again? And over time, this power is stable or decreased? For a long time running, what happens?
Not yet agree about 1,000. This 1,000.
Hours.
I don't understand how you got the stable power level for 1,000 hours. What did you do to get the stable power level?
Of course, we have some not secret, but after the past we are publish such secret. After that, you can read.
Is there a correlation between the energy and the number of helium atoms?
Energy and what?
Number of helium atoms.
Energy.
He says, presently, he just raised the temperature to the 1,300 degree centigrade, and then the helium gas evacuate, the emission from the palladium black, and therefore the relation between the number of helium and the energy is not confirmed yet, but he is quite sure it will be.
Because inside double structure cathode, not yet so high temperature, not yet finished. So from now, we establish, we make so more higher temperature over this cathode, or this cathode. You understand?
How long will it take for it to evolve?
Very nice work. What is the power density, for example, watts per gram palladium?
For example, now we use 3 to 5 gram the palladium black inside this cathode. At that time, about continually 10 watt, 12 watt appeared. Okay, you can.
Yes, I was wondering if you saw any new element formation in the palladium after you did your experiment.
Could you say that?
I was wondering if you saw any new element formation in the palladium after the experiment was over. If you checked it for other elements.
That's nothing. At present, nothing.
What did you say?
The answer. No, what was the answer?
We can't hear it.
Nothing.
Nothing. Any other questions? May I ask one? Yeah, your case, you said you didn't see the helium-3 emission. No helium-3. Well, Mach3 is almost HD.
Now, I think almost M3 DH, but if M3 a little not yet can decide. So,
thank you very much. Now, let's hand to and we'll move to the next speaker. Next speaker is Dr. Miles from the United States. He will talk about his colorimetric studies of palladium alloy cathode. Please.
to talk, is this on? My talk today is on work I did in Japan. I work for the Navy, but since 1995 the Navy has not funded this area, so this is the only work I've done on cold fusion in the past 5 years. Was 5 months in Japan working at the New Hydrogen Energy Laboratory. I tried to collect as much data as I could in those 5 months. I knew I'd have a lot of time when I got back maybe to analyze the data later, to look at the data and analyze it. And I'm still in the process of analyzing all the data I collected from Japan, and Martin Fleischman is helping with some of the analysis he'll speak on tomorrow about some of the data. I took with me to Japan my China Lake type cells, where the heat is transferred by conduction. I'm not going to talk about that today except to just summarize it. The first 2 experiments were 2 rods I'd run in China Lake. This one had given excess heat before. It gave excess heat again in Japan. This one did not give excess heat in China Lake, and it did not give excess heat in Japan either. And then I tried platinum particles and palladium particles, excess heat with the palladium particles, but none with the platinum particles. And this was a continuation of the same experiment where I went to a different type of electrolysis instead of constant current of pulse with Dr. Tripodi's help. And the excess heat got larger, as you see, and still no excess heat in the platinum material. So this just summarizes very briefly the China Lake calorimetry. At all times I had 5 calorimeters running, 2 of my own from China Lake and 3 of the Fleischmann Pons type, and that will be the focus of my talk today, is the Fleischmann Pons calorimetry. But before I go into that, the China Lake calorimetry has been published. This came out just recently in Journal of Electroanalytical Chemistry, the February 29th issue of this year, 2000. I have some reprints with me I can give people if you're interested. If I run out, give me your card and I will send you a copy of this in the February issue of Journal of Electroanalytical Chemistry. I was surprised by that paper because both referees agreed to publication. I did not have much trouble. That's unusual in this field. The Fleischmann Pons calorimetry, I ran various experiments. Some rods I took with me, these 2 were made by NRL, palladium cerium boron. The second one is palladium boron. The third one is the palladium cerium given to me previously by Martin Fleischmann. And that will be what I'm talking about today, these top 3. I also ran co-deposition. That's the Stan-Spock method, where you deposit palladium out of solution at the same time it's loaded with deuterium. All 3 of those produce excess heat. A preliminary report of this is published in Fusion Technology September 1999. But Stan Spock and I are still working on the exact analysis of this data and hope to have a more detailed publication later. And then also worked with Paulo Tripodi on electromigration using Fleischmann Pons cells, but we ran rather short of time to do very much details of that study. So anyway, my talk today is on the Fleischmann Pons calorimetry. These were cells shipped to Japan, similar to what Martin Fleischmann and Stan Pons had used previously in France. The cathode is here, of course, the anode, and it had 2 thermistors, a long thermistor and a short thermistor, so 2 temperature readings. Data was taken every 300 seconds or 5 minutes and recorded by data acquisition in the computer. But that's a typical Fleischmann Pons type cell arrangement. The 3 studies I will talk about today, the palladium cerium boron made by NRL. This is 4.4 by 20.05 millimeters area and volume shown there. The palladium boron, which had been very successful in China Lake in producing excess heat. I had 7 out of 8 produce excess heat prior to Japan. And this one also produced excess heat, as we'll see, in Japan as well. The palladium cerium was given to me by Martin Fleischmann, a few years earlier and produced excess heat in excess heat in China Lake. And I took it to Japan and produced excess heat also there. This is an earlier study on palladium boron. This was done at China Lake. One interesting feature shown here is excess heat starts very early, almost right at the beginning of the experiment, almost the first or second day. Excess heat starts to appear. We see this also in the results in Japan. Excess heat sets in very early in this palladium boron experiment. And throughout this time period, of course, there's considerable excess heat in the China Lake experiment, published in the China Lake publication as shown above. But it's important to note that the excess heat starts very early because we'll talk about that a little bit more later. The palladium cerium also produced excess heat in China Lake. This is from the Navy report in the 1994, 1995. Well, this is 1994 the data shown here, but it showed considerable excess heat, the palladium cerium rod. I used exactly the same rod again in Japan and also got excess heat. The palladium boron was a different palladium boron rod that I used in Japan than what I showed previously, however. Now this is the mathematics, and I don't know how much time I should take on this, but this is the power of the calorimeter. The power that goes in is the electrical power and any excess power, if it's present. The heater power, when the heater is applied. The power going out is the heat lost due to radiation. Most of the heat transfer in this calorimeter is by radiation, in contrast to China Lake, where the heat is lost by conduction, and the power carried away by the gas stream. So that is your equation, but the terms get rather complicated. That's the electrical power in, that's the thermal neutral potential, the Faraday efficiency, which is 1 in all cases that I've ever ran. The power out, since this radiative transfer is the t to the 4th, and the radiative heat transfer coefficient. The power of the gas stream is rather complicated, but involves heat capacities of the various gas species, deuterium gas, oxygen gas, D2O vapor leaving the cell, as well as the largest term actually is the power lost by evaporation, D2O changing from liquid to gas. That turns out to be the largest term there. The power of the calorimetry is this term right here. But the point I want to make is to do calorimetry accurately with this system, you have to have accurate values for the cell, the radiative heat transfer coefficient, and what is called the water equivalent of the cell, the mass times the heat capacity of the cell. And these are the two areas where the Japan analysis by NHE fell short. That they did not establish good values for these key parameters. You cannot have accurate calorimetry unless you have those two parameters determined accurately. The radiative heat transfer coefficient and the water equivalent of the cell. Those are basically your two unknowns. The rest of these things you can calculate or measure. The way I do the calculations is I calculate all these heat capacity values at the temperature measured for the cell, because they can be expressed, this is from the literature, how these values vary with temperature, the various heat capacities, the heat of vaporization, how it varies with temperature, the vapor pressure of D2O, how it varies with temperature, and because it's an LiOH, so the LiOD solution is, I multiply by 0.98 there, and the thermal neutral potential, how it varies with temperature. So I actually calculate all these values at the temperature of the measurement of the cell. And this can be easily done through modern computers using Excel spreadsheets. These equations are rather complicated, but computers handle them fairly easily. Now the time constant of the Fleischmann-Pons calorimetry is about 90 minutes. Therefore, you need to average the data. I want to point out, just if you don't average the data and take one data point, some error sources. The heat capacity of the water equivalent of the cell is 450 joules per degree. If you have an error in measurement from one point to another of only 1/100th of a degree, and multiply those two together, the data is taken every 300 seconds, you see an error of plus or minus 15 milliwatts. So that's purely because you're not averaging the data. This is all these errors are removed by averaging the data. The cell doesn't respond quickly to any change. It responds over a very long time period because it takes 90 minutes just to reach the time constant. And it takes several hours to reach a new equilibrium after you change a parameter like the cell current or add D2O. It takes several hours to come back to a near equilibrium. Your cell voltage measures due to gas bubbles, and you may have between two measurements plus or minus 2/100ths of a volt. If you're running at 500 milliamps, that's an error of plus or minus 10 milliwatts. But if you average data, these errors are not are removed because your cell is averaging all the time. It's averaging everything that's going into it over a long time period. So because the cell is averaging the effects on it, you should average measurements that you make, and perhaps also measure the temperature to a thousandth of a degree, for example. That would help also, which we did in the data we had in Japan. Now the NHE method, in my opinion, was very poor, fell far short of being accurate because it did not determine this radiative heat transfer coefficient accurately or the water equivalent of the cell. In fact, they just assumed a value for the water equivalent of the cell, to the best of my knowledge. They determined the heat transfer coefficient by the first application of the heater pulse. First time the heater was turned on, they calibrated for the entire experiment based on that first and only heating a cycle. And that's basing your whole experiment on one calibration, which is very incorrect in my opinion, because if anything is wrong with that one calibration, the whole experiment is off. And that's exactly what they did. They took the first cycle and used that to calibrate for the cell constant. You should do extensive work to determine what that cell constant is and make sure it's consistent throughout the experiment if you want accurate results. Even when they did apply the resistive heater, it was for too short a time period, only for 6 hours. For the time constant of these cells, you don't really quite get to equilibrium, so you don't get really a good measurement because the time period is too short. It should be applied more like 12 hours instead of 6 hours. They assumed a value of the water equivalent of the cell. I think it's actually 490 is what they assumed. And I don't know where they got that value, but they just used that in their computer calculations as the water equivalent of the cell, which is off. As far as I can tell, they did not average the data sufficiently. Martin Fleischmann Stan Ponce had a handbook there that talks about averaging the data for 11 measurements or for over 55 minutes. You should use an average, either backward averaging or forward averaging, using 11 points, which would be over a 55-minute time span. But to my knowledge, NHE ignored that and used their own methods without this averaging taking place. I'm not aware of any blank experiments they ran to check that the calorimetry was performing properly based on the way they did their calculations. They should have ran blank cells using platinum cathodes with D2O, for example. And there was no measurement of atmospheric pressure at the laboratory. In the equation for the calorimetry, there is an expression that involves the vapor pressure of D2O and the atmospheric pressure. So you need to know what the atmospheric pressure is day by day to do these calculations, especially if you go to the boil off. That's very important. This is data from Martin Fleischmann using my data I gave him from Japan on the palladium boron. This is a heating cycle that Japan based their calibration on. This is the cell temperature. It's gradually going down. You apply the heating cycle, the temperature goes up, but you see it doesn't really reach an equilibrium. The time period is too short. And furthermore, when you turn the heater off, it does not relax completely back to what the baseline should have been. If you put a straight edge here, maybe you can't see it from here, but it should come back to the same baseline, which would be about right here. The temperature does not come back to that baseline, showing there was positive feedback. And you had excess heat during that heating cycle, and that continued after you turned the heating cycle off. And that's also a reason why this didn't level out very good up here, because excess heat was being produced, and it was increasing as you were increasing the temperature. So they could not in any way get a good calibration based on that heating cycle. And that is the only heating cycle they used in the entire experiment to get the radiative heat transfer coefficient, which is completely wrong. They got a wrong constant, and therefore a wrong result. This is the cell voltage. Of course, when the temperature goes up, the cell voltage goes down, as you would expect. And then when the temperature starts to fall, the cell voltage goes up again. But you should look at heating cycles like this and look for evidence of positive feedback. And before you determine, you can use that for the calibration. This is data I plotted out of another heating cycle. We turn on the calibration heater comes on. Here it does level out better because there's no positive feedback, or very little in this case. And you see it relaxes back. I do a straight line here, and it relaxes back to about the same baseline. So in this case, it looks like there was not a serious problem, perhaps, with positive feedback. Again, the cell voltage, when the temperature goes up, the cell voltage goes down. But it comes back to about the same basis. You can see you need to average the cell voltage because of the fluctuations it goes through. You have to use an average value for cell voltage. I plotted this out point by point on large chart paper. This is rather tedious. It takes maybe 2 hours to plot a data point like this, but it's a good exercise to test what's going on in your system. In the limited time I have in Japan, only 5 months, and running 5 different experiments, I did not have time to work out details of exact analysis. I knew that the way NHE was doing it was wrong. I did not want to just let it go on what they were telling me. So I tried to find my own method, which is not as good as Fleischmann's, but I think it worked to some degree. I used exact calorimetric equations with no approximation starting out. I tried to use near steady-state conditions where the water equivalent errors would be minimized because the change of temperature is very small. So I used time periods where the cell had reached near equilibrium. And the temperature was not changing rapidly. Therefore, errors due to the water equivalent term would not be too large. And then I used an estimated value for that, since I had no way of determining it exactly. Japan told me it was 490, but Martin later found out in his data found out it was 450. So 450 should have been the value instead of 490. I determined a pseudo-radiative heat transfer coefficient by assuming there's no excess heat. And then I found periods where these heat transfer coefficients, assuming no excess heat, are high. Those would be periods where the excess heat was either low, because excess heat will make your values, the heat transfer coefficient, go down if you assume there's no excess power. So I calculated the heat transfer coefficient and then used periods where it were high, where therefore the excess heat would be small or zero, and used that for my heat transfer coefficient as an approximation. And then I used this value going back into the equation to calculate what the excess power would be. So the first experiment I did this on was the palladium cerium boron alloy. This was my heat transfer coefficient that I came up with, and I used this value, which is too high. I found out later, but I used this value. But I used data where the temperature change was small, so this would not be a big error. And for the palladium cerium boron, there's not much excess power. So this showed that this method was working to approximate degree at least. There's no significant excess power. There are fluctuations, but no large excess power effects using the method I worked out while I was in Japan. Now, when I applied the same method to the palladium boron, I got a different result. There was excess power. There's even a small excess power even starting out early in the experiment, but there were two large bands of excess power. A large band through here, through this region, and then less excess power through a large time period, and then another band of excess power later in the experiment. And using this value. Now, as Martin Fleischman will mention tomorrow, perhaps this constant is too small. It should be around 8.5 instead of 8.1. And this value should be around 450. But I do have the data